In this video, we're going to talk about antiderivatives and the indefinite integral. Um, and so we've been focusing on the definite integral and the indefinite integral, which is what creates the functions that we could use in order to evaluate or find the definite integral, is related to what we call antiderivatives. And so let's define an antiderivative. As you can see here, an antiderivative of a function f of x is the function that has f of x as its derivative. So it's kind of like the undoing of a derivative. That's why we call it an antiderivative. In this section of our notes, we're going to denote the antiderivative as capital F of x. And so let's try to wrap our minds around what's going on here when we find the antiderivative. It says if f of x equals 2x, what is capital F of x, or the antiderivative? So what we should be thinking about is what function exists such that if I do its derivative, I'm going to end up with the expression 2x, right? And so remember your rules of differentiation or finding the derivative of a function when it's written in this algebraic representation. Remember, a function that looks like this comes from doing the derivative of something that looks like this, x squared, right? Because in order for me to get 2x, right, and I can check myself, right? A good check is to take the derivative of what you think your antiderivative is. And if you end up with what you start with, which is this little capital F of x, then you found the actual antiderivative. And so if I look at f of x equals x squared, we bring that 2 out front and we reduce the power by 1. We don't have to write that 1 in the exponent there. And so we get f prime of x equals 2x, which is what we started with. Therefore, the antiderivative of f of x equals 2x is x squared. Now, are there any other functions that will work for the antiderivative in example 1? And I'm going to submit to you that there are other antiderivatives. For instance, if I look at f of x equals x squared minus 8, for instance, when I do the derivative of that, if I get the same thing that I started with, then this is also an antiderivative of f of x equals 2x, right? And so if I take the derivative of this, I'm going to get 2x. If I take the derivative of that minus 8, that derivative is 0 since it is a constant. So this too is an antiderivative of f of x equals 2x. I can give you another example. For instance, if I let my antiderivative, if I assume that x squared equals x, f of x equals x squared plus 3. When I take the derivative of what I think is my antiderivative, if I get started or start back with what I started with, I should get 2x. Well, the derivative of x squared is 2x. The derivative of 3 is 0. So I found another antiderivative, right? In fact, I can change this number that is a constant here to any number that I can think of, and leave that x squared plus or minus that number, and then I'm also going to have an antiderivative. And so what happens here is that we have a family of functions that are actually the antiderivative of a single function, and they all differ by a constant. And so we can write the most general antiderivatives of 2x, that function f of x equals 2x, as f of x equals x squared plus, and I'm going to say capital C, right? This is used everywhere in calculus, where this C equals your constant of integration. All right. And so all of the antiderivatives of f of x equals 2x come in the form f of x equals x squared plus c. Capital F of x equals x squared plus c. And so we're going to start seeing that added c, that plus c there, to denote that this function is not the only function. I have a family of functions that differ by that constant c. So anytime we find the antiderivative of a function, we need to add that plus c, all right? And so let's look at some more examples of where we find some antiderivatives so that we can kind of wrap our heads around this. Remember, we're always undoing the derivative. So we find a function whose derivative is sitting there, right? So in part A, I have f of x equals 7. This is a constant function. I got to think of which function has the derivative of 7, right? Or 7, well, 7, right? And so the only function that I can think of, well, there's an infinite number, right? But when I think about variable expressions, that's going to come from a linear function because the derivative of linear functions is the slope, right? And so it has to come from a linear function with a slope of 7. So I get 7x, but it can have any constant. It can be 7x plus 8, 7x minus 3, 7x minus 17, 7x plus 17, right? So I have to add that constant c. And remember, you can always check to see if you got the correct antiderivative by finding the derivative of your antiderivative. And if you get what you started with, you're going to be correct. The derivative of 7x is 7. The derivative of a constant is 0. So I get 7 plus 0, which is exactly what I started with. Let's go to part B. I got to think about which function exists such that if I take its derivative, I get 3x squared plus 1. Well, that's going to be coming from a polynomial function. If I take x squared, 3x squared, that looks like I brought the 3 out front and reduced the power by 1 and get 3x squared, right? So that looks like I used 3x cubed as my function. And so notice in the second term, I have a constant again. The derivative of a linear function is a constant, and that constant is the slope. So it's just going to be plus x. Remember, this is a family of functions, so I have to add my constant of integration. And so I get x cubed plus x plus c. Again, we can check ourselves by doing the derivative of what I think my antiderivative is. And if I get f of x, which is what I started with, then I've chosen the correct function. So that I bring that 3 out front. I reduce my exponent by 1. I get 3x squared. This is a linear function. The derivative of that is 1. And this is a constant. The derivative of a constant is 0. And so that checks out perfectly. So I have my correct antiderivative, right? So this is my answer here for the antiderivative. And I guess I can go back and do that for this example here. All right. We're going to skip C because it's a little bit more difficult. And let's go to example D. I have f of x equals 4 plus e to the x, right? I want to find the antiderivative, right? Well, I'm going to go term by term, right? My first function or my first term is just a constant. Remember, the derivative of a linear function gives you a constant, and that constant is the slope of that linear function. So I'm going to write something that looks linear. Remember, the derivative of e to the x is e to the x, right? So if I undo its derivative, I get its antiderivative. This is one of my favorite. Find the derivative of and find the antiderivative of, right? Because it equals its derivative, so it's going to equal its antiderivative as well. Notice we have to put that plus c, and then I'm not going to check this one this time, but you can take the derivative of 4x and you're going to get 4. You take the derivative of e to the x, you get e to the x. You take the derivative of this constant c and you're going to get 0, which is what you start with. All right. Now, these examples follow straight from the rules of differentiation, right? We want to get more general. And so let's look at this example C here. I have f of x equals x squared plus x. I want to know which function exists such that if I take the derivative of it, I'm going to get x squared plus x. That's what it means to find the antiderivative. And so if I think about this, well, in order for me to get an x squared, when I take the derivative of something, I've got to start with a power that's more than x squared, one more than x squared, right? Which would be an x cubed. Now, if I were to take the derivative of x cubed, right? If I took the derivative of that, now I'm just going to do some thinking here. So if you don't want to write this down, that's fine. If I take the derivative of this, I just put, well, I guess I should say d dx instead of putting prime, because that's more mathematically perfect. All right, then this equals 3x squared. So x cubed doesn't work for me here because if I do the derivative of x cubed, I'm going to end up with 3x squared. But this does not have a 3 in it, right? My function doesn't have a 3 in it, right? So I need to get rid of this 3 that's multiplied by the x squared. And if I do, I end up with what I started with in the function in which I'm trying to find the antiderivative of, right? So what we're going to have to do is to undo this. This is a multiplication by 3. We're going to have to divide by 3. So I divide that by 3. And notice if I were to divide this by 3, right, that's the same thing as 1/3 x cubed. We will bring this 3 out front and multiply by 1/3, and we're going to get a 1. And we reduce that exponent by 1, we get a squared, right? And so we're going to have to actually undo that multiplication by 3 that our normal power rule requires by dividing by 3. So my antiderivative that will give me this x squared here is x cubed over 3, right? I increased this exponent by 1 and I divided that power by that same exponent there, right? Let's go to the second term here. There's a 1 understood to be that power, right? Now, in order for me to get a derivative of a function and it be x to the first power, I would have had to have brought down a 2 in front of that and reduced and rose it to the 2 minus 1, which is the first power, right? So it's going to be an x squared in here because when I do the derivative of x squared, I get 2x. This does not have a 2. So I have to undo that 2 in my antiderivative, and that would allow me to get the actual antiderivative, right? And so notice there's sort of a pattern here. In both of these x to a power, what we did here was we increased the power by 1 and we divided by that same power. Here, I increased power by 1, I got 3, divided by 3 to get the antiderivative. Here, increase that power by 1, I get x squared, divide that by that same power, I get that, and I have to add my constant of integration. Now, just to make sure that we did that right, I'm going to check this because I know some of y'all don't believe me. I'm just kidding. All right. Now, if I do the derivative of f prime of x, the antiderivative, right? This is like a 1/3, right? So you could write this antiderivative. I'm going to slide over some since I'm running out of space. You could always write this as 1/3 x cubed plus 1/2 x squared plus c. That's another way to write that, right? So when I do my derivative of my antiderivative to see if it really is in fact the correct antiderivative, I'm going to write it as 1/3, and then I do the derivative of x cubed, which is 3x squared. I'm going to go to my next term, 1/2, and then I'm going to write the derivative of 1/2 of x squared, which is 2x, and the derivative of that constant is 0. And so notice this 1/3 and that 3 cancel, and I'm left with an x squared. That 1/2 and that 2 cancel, and I'm left with an x. It's a plus x because there's a plus sign in between there. And then that plus 0 I don't need to write. And this is exactly what we started with. And so this gives us a rule for finding the antiderivative of x to a power, right? That's one of the most important rules that we're going to have. We're going to have an antiderivative rule for when we have a constant, an antiderivative rule when we have x to a power, which applies to this. I'm going to circle all of them that it applies to. This here, and this here. And then we have an e to the x antiderivative, which is e to the x. And we also have the natural log antiderivative. It doesn't have the natural log in it, but its solution has the natural log. And we're going to write all these rules down. All right. Before we get there, I want to return to talking about the integral, right? What we were doing before in the previous chapters were previous sections is we looked at definite integrals. Definite integrals are integrals with limits of integration, right? Integral from a to b of f of x dx. This always equals some number. Okay? Notice it has limits of integration. It has limits of integration. What we're going to do now is we're going to talk about indefinite integrals, right? The integral of f of x dx equals the antiderivative of f of x, which we call capital F of x, if f of x is the antiderivative of f, right? And so when we don't have limits of integration, we actually have a function, right? This is a whole function. This is a function of x. When we do have limits of integration, this is a number, right? This is called the indefinite integral because there are no limits of integration. All right. And so what we have to do in order to find the indefinite integral is the exact same thing that we did when we found these antiderivatives here. We're going to use these rules that we kind of discussed and derived here, and we're going to apply them in a formula, right? Notice in each of these expressions here, we have an antiderivative, an indefinite integral, right? And it's indefinite because there are no limits of integration. But the integral of x to the n, this is almost like your power rule, right? Power rule. This is equal to x to the n plus 1 over n plus 1 plus c. Now, for all n except n equals -1. This rule right here works for any n except for n equals -1. And I want you to look at why. If n equaled -1, then if we use this formula here, we get -1 plus 1 in our denominator, which would be 0, and we could never divide by 0. Now, we're going to see that when n does equal -1, we actually have another antiderivative, right? And if you think about it, what function has a derivative of 1 over x? That function is the natural log of x. We got to put our plus c. Now, when we see this formula here, because we don't know the value of x, we always put, and you cannot take a natural log or any logarithm at a negative number or a non-positive number actually. So we usually just put this x in absolute value to ensure that that is always positive, so that the variable is always in the domain of that function. All right. So we have a power rule here for antiderivatives. You increase the exponent by 1 and divide by that same power. This is exactly what we did in this example here with x squared and x to the first power. We did x cubed over 3. We did x squared over 2. We did the same thing here, right? You increase your exponent by 2. 2 plus 1 is, you increase your exponent by 1, sorry. 2 plus 1 is 3, and you divide by that 3, you're going to get, that 3's are going to cancel, and you're going to get x cubed, all right? So that's your power rule, and this is the rule that's related to your natural logarithm. If you take the indefinite integral of a constant, it is like a linear function because the derivative of a linear function is a constant. So it's going to be k times your variable x plus c. That's your formula there. The derivative of e to the x is e to the x, so the antiderivative of e to the x is e to the x, so we get e to the x plus c. And then these other rules come from some of the properties that we talked about when we looked at derivatives. For instance, when we have the antiderivative of a sum, right? Well, when we had the derivative of a sum of two numbers or two functions or a subtraction of two functions, we were just able to do the derivative separately. And so since the antiderivative, if we do its derivative, we get the function that we started with, the same stuff applies, right? So the integral of f of x plus g of x dx is going to be the integral taken separately. It's going to be an integral of f of x dx plus the integral of g of x dx. And then if there's a subtraction, then it's going to be a subtraction. All right. Notice here we have a constant. K is a constant, and f of x is our function. If we have the integral of k times f of x, again, when we had a derivative of a number multiplied by a function, that number stayed in that derivative multiplied, right? So it's almost like we can bring out that constant and do the integral of f of x dx. All right, and this is going to be our antiderivative there. All right. And so these are the rules that we're going to cover so far, and let's look at some examples where we apply these rules here. And so example 3, we're going to start with this first example here. Find the indefinite integrals, right? When I have indefinite integrals, I'm going to end up with a function, right? If I were to add limits of integration, I'll be able to find a number, right? You put this in your calculator actually will give you a number, but it's going to be an incorrect number, okay? When you don't have limits of integration. All right, and so actually, I don't know if your calculator will give you a number because you're going to have to put A and B in for your limits of integration on your calculator for it to give you something. So notice your calculator won't give you this, so you need to know how to do this by hand. And so here we go. I have the indefinite integral of 2x minus 1 dx. Now, what we could do is we could actually apply these rules stringently. I'm going to do this on this example, but for the other examples, I'm not going to do it, okay? If I want to do this antiderivative, right? Well, there's a minus, so I can look at the integral of 2x dx minus the integral of 1 dx, right? And then that 2 is multiplied by this function x. So I can do 2, bring that 2 out of my integral and do x dx, right? Minus the integral of 1 dx. So now I can take my antiderivative, right? Well, this is a 2 here, so that 2 is going to stay there. There's that constant multiple rule. And the antiderivative of x to the first power, well, I increase that power by 1, which is 2, and I divide by 2, and that's going to give me my antiderivative. And the derivative of constant is that constant times x. Now, I could put a plus c here after this antiderivative or this indefinite integral, and I could put a plus c here. But usually when we have more than one term, we just put 1 plus c in the overall antiderivative. And so the 2's cancel here. We get x squared minus 1 times x is just x, and then I have my plus c here. And so my indefinite integral of 2x minus 1 dx is x squared minus x plus c. All right. Now, you do not have to go through this entire step here, right? You could have just started at this step, taking your antiderivative, and you'd get your answer, all right? Which is what I'm going to do in example B here, all right? So when I do this antiderivative, all right, my first term is x to the 7. So I'm going to do x to the 7 plus 1, which is 8, over that same exponent. Plus, notice this is 5 times something, right? So I'm going to write that 5, and I'm going to focus on doing the antiderivative of x squared. Well, I increase that exponent by 1, which will give me a 3, and I divide by that same value, right? I have minus 8. That is a constant multiplied by the x. This is x to the first power. So when I do that antiderivative, it's going to be x to the 1 plus 1, or 2 over 2. Plus the derivative of this constant here. This constant here is, the antiderivative of this constant here is that constant times x. And then I'm going to have a plus c. And since I wrote that so big, I'm going to move this over a bit. And then I'll simplify it. And so this is going to equal, if you wanted to write this as 1/8 x to the 8th, that's perfectly fine, plus 5/3 x cubed. 8 divided by 2 is 4, so that'll be a minus 4x squared plus 2x, and then I have to add on my plus c, right? This is the antiderivative. We don't use a capital F of x here because this is what this indefinite integral equals. Let's go to part C. I have the integral of 7 over x plus the square root of x, right? Notice here, if I were to rewrite this, this would be 7x to the negative 1. All right. Usually when my variable is in the denominator, I'm going to want to bring it out of the denominator so that I can use this rule right here. But remember, this rule only works for any n except -1. And so when I bring it out of the denominator, it's the x to the -1, which that power rule does not work for, because if I were to try to take the antiderivative by adding 1 to the exponent, I'm going to get x to the 0 over 0, and division by 0 does not make sense, okay? And so we have to remember that we're going to leave this, and I'm going to write it slightly different. I'm going to write it as 7 times 1 over x so that we could really see it, right? Remember, this is like 7 over 1 times 1 over x, right? And this second term over here is x to the 1/2. Now, the reason why I wrote it as x to the 1/2 is the same reason why I would do that if I were taking the derivative, so that we can see the actual power. Now, this first term right here has to do with our logarithms, right? because we have this rule here that antiderivative or indefinite integral of 1 over x dx, the natural log of absolute value of x. And so since that 7 is multiplied there, the 7 is still going to be multiplied. It's going to be times the natural log of the absolute value of x. And then when I go to this term here, it's going to be, all right, I'm going to write this out, x to the 1/2 plus 1 over 1/2 plus 1, and I have plus c. Now, that 1/2 plus 1 is 3/2. So I'm dividing by 3/2, right? And when you divide by a fraction, you multiply by its reciprocal. So the reciprocal of 3/2 is flipping that. That'll be 2/3, and I get x to the 3/2 plus c. So that's my indefinite integral in that example. And then last but not least, let's look at part D here. I have this function here who I want to find the antiderivative for. What I'm going to do first is I'm going to bring those x's out from the denominator and from under this radical. I'm only going to do that if in the denominator it's not x to the first power, right? This first term is going to stay the same. But this will be a 1 over x to the 1/3. And so if I bring that out of the denominator, it's going to be an x to the negative 1/3. All right. And so since this is 8 over x cubed, I can write that as 8x to the negative 3rd power dx. And so now I'm ready to apply my rules so I can do my antiderivative, right? And so this is going to equal 3 times x to the 10th over 10 plus x to the negative 1/3 plus 1. Negative 1/3 plus 1 is actually 2/3. And I divide that by 2/3. Uh-oh, 2/3. Definitely hard to see that. So let's make that better. And then it's plus 8 times x to the negative 3rd plus 1. Negative 3 plus 1 is actually negative 2. And we divide by that same exponent. And then we'll have our plus c here. And so we can clean this up again. That's 3 over 1 or 3/10 x to the 10th. Plus, notice here, if I divide by a fraction, I multiply by its reciprocal. So we get 3/2 x to the 2/3. And 8 divided by 2 is 4. And that, my friends, is our antiderivative. All right, and so this concludes this video, right? We're using our antiderivative, right? The goal of doing antiderivatives is to undo differentiation. Find a function that exists such that if you did the derivative of it, you'd get the antiderivative. Sorry, if you did the derivative of it, you'll get the function that you started with. This concludes this video. Have a great day.